Welcome to the deep dive. We're here to extract the really key insights from important sources to help you get genuinely well-informed.
That's the goal.
And today, we are plunging into a topic that, well, it literally holds the future of our coastlines in its icy grip. Antarctica. I mean, just consider this. It holds enough frozen water to raise global sea levels by something like 190 feet. It's staggering.
It really is. And the way that colossal ice sheet moves, how it melts, it directly impacts coastal communities, everywhere.
So our mission in this deep dive is to really pull out the crucial insights about what's actually happening down there with Antarctic ice and, importantly, what it means for all of us.
Yeah.
We've got some cutting-edge research today, studies from Stanford, Dartmouth, the UK, and also a really important paper from the Asian Development Bank looking at the global economic side of things.
It's a critical mission, because trying to predict how Antarctica's ice will move and melt, it's just incredibly complex. Right. Traditional climate models have, frankly, struggled with this for a long time. Mostly because there isn't a lot of data from down there. And you've got these really intricate interactions going on constantly between the ocean, the atmosphere, and the ice itself.
It's a massive system.
Exactly.
Yeah.
So it brings up a really key question.
Yeah.
How do we even start to get a clearer picture? How do we model something that vast and dynamic?
That really is the million-dollar question, isn't it? And that's where this recent Stanford study comes in. They're using something powerful to try and cut through all that complexity, machine learning. So tell us, what exactly did they do? And maybe more importantly, what new things did this approach tell us about, well, the fundamental physics of how ice moves?
Okay, so what's really fascinating here is how the Stanford researchers did this. They combined what they call physics-informed deep learning.
Okay.
Which basically means training an AI using both huge amounts of data and the known laws of physics. So the AI isn't just pattern matching, it understands the underlying rule.
Right, it's constrained by physics.
Exactly. They fed it high-resolution satellite imagery and airplane radar data gathered over, 10 years?
Yeah.
2007 to 2018.
A lot of data.
A huge amount. And instead of trying to model every single tiny crack or air bubble in the ice, which, would be basically impossible.
Practical, yeah.
They focused on the large-scale movements, how the big sections flow, and this allowed them to work out new constitutive models.
Constitutive models, so like the basic rules for how this specific ice behaves.
Precisely. Think of it like finding the unique recipe or fingerprint for Antarctic ice, how it bends, stretches, and flows under different kinds of pressure. It's not generic ice.
So we were maybe using a more generic recipe before. What did the AI tell them that, say, traditional lab experiments or the older models were missing about Antarctica's specific ice?
Well, stepping back, it's actually quite a breakthrough. Existing models, they typically relied on assumptions about how ice behaves based on lab experiments, small samples.
Right, controlled conditions.
Yeah, but real Antarctic ice formed from seawater or snow packed down over millennia, full of natural cracks, variations. It just behaves differently when you look at the massive scale.
Makes sense.
So the Stanford team focused on 5 specific ice shelves. These are the huge floating platforms of ice that stick out from the land over the ocean. And crucially, they act like dams, holding back the glaciers on land.
The breaks, essentially.
They're the breaks. And they found that only a really small part, actually less than 5% of the ice shelf, the bit right near the continent, that part behaves like the lab tests suggested. It's compressed, squeezed.
Okay, only 5%. So if our whole understanding of how these massive ice shelves flow was based on experiments that only reflected 5% of their behavior, what does that mean for basically every prediction we have ever made about their stability?
Exactly. You've hit the nail on the head. The other 95% of the ice shelf is what they call the extension zone. That's where it's being pulled, stretched out towards the sea.
Right.
And in that zone, the ice shows something called anisotropy.
Anisotropy.
It just means its physical properties, like how easily it flows, are different depending on the direction of the stress.
Okay, you used the analogy of wood grain earlier. It splits easier along the grain.
That's a perfect way to think about it. But before this study, the models pretty much assumed the ice properties were the same in all directions, isotropic.
Oh.
As Qingyao Lai, one of the senior authors, put it, we combined that extensive observational data set with physics-informed deep learning to gain new insights about the behavior of ice in its natural environment.
So this isn't just some, minor correction factor. It's a fundamental shift in understanding how the ice works. What does knowing about this anisotropy mean for building future climate models? How does it change things?
It means that the current models, well, they aren't accurately capturing how the ice sheet actually moves
Yeah.
when you compare their output to what satellites are showing us.
They don't match reality.
Not as well as they should. Another researcher on the study, Young-Hee Wang, said, people thought about this before, but it had never been validated. Now, based on this new method, we know that models predicting the future evolution of Antarctica should be anisotropic.
So future models need to build this in.
Absolutely. This work is really the first critical step towards building much more accurate models that can hopefully simulate future conditions better.
Yeah.
And this whole technique combining physics with AI on large data sets, it could potentially unlock insights into other complex natural systems too.
Really interesting. So, okay, we have this new, more accurate understanding of how the ice is moving thanks to AI. The next big question is obviously, how much is going to move and how soon? And that leads us right into another major study, this one led by Dartmouth College, involving, what, over 50 climate scientists?
Yeah, a big collaboration.
And they took a really long view, looking way beyond 2100, which is often where policy discussions tend to stop. What did they find about the trajectory of Antarctic ice loss further out?
Yeah, this really highlights a potential issue with focusing only on the next 80 years or so.
Right.
The Dartmouth study pooled data from 16 different ice sheet models, and they project, generally, a gradual, fairly steady increase in Antarctic ice loss up to 2100.
Okay, steady, but then
But after 2100, the picture changes dramatically.
dramatically how? What sort of acceleration are we potentially looking at? And I guess, how confident can we be in projections that far into the future?
Well, under the high emission scenarios, so if we don't significantly curb greenhouse gases,
Business as usual, kind of.
sort of, yeah, the models show a rapid retreat of glaciers in western Antarctica, kicking in around 2200. This could potentially raise global sea levels by as much as 5.5 feet just from that acceleration.
5.5 feet just from Antarctica by 2200.
From that West Antarctic acceleration, yes.
Yeah.
And by 2300, some models even suggest the near total collapse of Antarctica's ice sheet becomes possible, though that's further out and has more uncertainty. The lead author, Helene Sarusi, she really emphasized that policymakers often focus on 2100, but their study gives these longer-term projections that have been lacking, and she said, beyond 2100, the long-term impact become amplified.
So the consequences get much bigger later on. What about confidence? Long-range models always have uncertainties, right?
Absolutely, and especially with something as complex as ice sheets. But the key thing here is the consistency across many different models. While the exact timing might vary a bit, they generally agree on this accelerated loss in West Antarctica under high emissions. That consistency boosts the confidence in the overall message.
And what about the role of carbon emissions specifically in driving this? Does this study really show that our actions today have these multi-century consequences?
Oh, absolutely. The study makes that crystal clear. The difference in predicted sea level rise between high-emission pathways and low-emission pathways becomes much, much larger after 2100.
So the paths really diverge then.
They really diverge. Under high emissions, certain big basins in western Antarctica could cross a threshold into what's called irreversible ice loss,
Irreversible meaning.
meaning that once it hits that tipping point, the melting becomes rapid and basically unstoppable, even if we were to drastically cut emissions after that point. It's locked in,
A runaway effect.
essentially.
Yeah.
Matthew Morlem, one of the co-authors, put it bluntly, it is critical to cut carbon emissions now to protect future generations. As you said, the timing varied model to model, but the rapid pace, once it starts, was consistent.
Okay, so we have the big picture long-term view. Now, if we want to zoom in even closer, maybe look at specific sectors within Antarctica that might be vulnerable, there's this groundbreaking UK Earth system model. It gives even more detailed simulations, right? What did that reveal?
Yes, this UKSUM 1.0 ice model is really significant. It's the first time a top-tier, state-of-the-art global climate model has been fully coupled with an ice sheet model.
Coupled means they talk to each other in the simulation.
Exactly. Instead of running climate scenarios and then separately feeding that data into an ice model, this setup lets the atmosphere, the oceans, and the ice sheet interact directly within the simulation in real time. It gives a much more holistic, hopefully more realistic picture.
Okay, so what did this more integrated model show?
Their projections show that, yes, most ice shelves thin over time, which we expect, but it also pinpointed specific areas where really strong melting could significantly accelerate later this century, specifically under high-emission scenarios.
And where were these areas?
Interestingly, under the Ross Ice Shelf and the Filchner Ice Shelf. Now, Based on modern observations, these haven't generally been considered the biggest immediate threats.
So potential surprises down the line.
It suggests we might see significant climate-driven changes popping up in sectors we aren't currently focused on as the main problem areas.
That's a really crucial detail. Now, the model also projected something else interesting, almost a 30% increase in snowfall onto the grounded ice sheet by the 2090s,
That's right.
especially in East and West Antarctica. So just to be clear for you listening, the grounded ice sheet is the massive part resting on land, not the floating shelves.
Correct. The vast majority of the ice.
How does this increased snowfall factor in? Does it balance out the melting?
That's a really important nuance. Yes, more snowfall on the grounded ice sheet adds mass back to Antarctica, and this can offset some of the ice being lost through melting, at least in certain places or for certain periods.
So it slows things down a bit.
It can act as a bit of a buffer. However, the overall consensus from these models, including the UK one, is that even with more snow, the melt rates, especially driven by warming ocean water eating away at the base of the ice shelves, are still projected to win out in the long run.
Ah, okay.
Particularly under those higher emission scenarios. So more snow helps, but it doesn't stop the overall trend of net ice loss predicted for the future. It just highlights how complex the whole balance is.
Okay, let's shift gears a bit and bring this closer to home for you, our listener. We've talked about the physics, the projections, but what does all this melting ice and rising sea level actually mean for people, for economies around the world?
Yeah, the ripple effects are just enormous. That Asian Development Bank study you mentioned earlier, it takes a hard look at the impacts of sea level rise, particularly on economic growth in developing Asia, but the implications are global.
And what did they find?
They estimated that global GDP loss by 2100 could range anywhere from 0.3%, which is still significant, up to a really staggering 9.3%.
Wow, 9.3% of global GDP wiped out. That's a huge potential range. What's driving such massive potential losses?
It comes from so many angles.
Yeah.
Rising seas directly threaten food security. Think saltwater intrusion into farmland, loss of coastal agriculture.
Yep.
Water security is also hit.
Right.
Critical infrastructure gets damaged or destroyed. Roads, bridges, ports, power plants near the coast. Public health suffers from waterborne diseases, displacement stress.
And livelihoods too, I imagine.
Definitely. Think about fisheries and aquaculture. Over 10% of the world's population relies on those for their livelihood. Rising seas, changing ocean chemistry, that's all compromised.
And just the basic fact of more flooding.
Exactly. Low-lying coastal areas face more frequent, more intense flooding. That means huge economic disruption, damage repairs, lost productivity, and, crucially, it forces people to move. Human migration.
Can you give us some specific examples, places already feeling this or places identified as particularly vulnerable?
Sure. It's vital to look at these regional vulnerabilities because it's not uniform. The ADB report mentions Davao in the Philippines, for instance. It's seen one of the highest measured sea level trends, anywhere about 5.3 millimeters per year.
Doesn't sound like much year to year, but...
Over a century, that adds up to over half a meter, about 1.7 feet. That's a huge change for a coastal city.
Yeah.
Then you have places like Singapore, a small, dense island nation, highly vulnerable. About 30% of its land is less than 5 meters or 16 feet above sea level. Some projections, considering warming effects too, suggest Singapore could eventually face sea level rise that puts maybe 745,000 homes at risk. Protecting its coastline is already costing millions, and that's projected to rise sharply.
And for other small island states?
For many, like Kiribati or Tuvalu in the Pacific, it's an existential threat. They face the real possibility of complete inundation within decades or a century under higher scenarios.
It really does underscore the urgency. You mentioned migration. What are the projections looking like for people being displaced by rising seas?
It's expected to be a major driver of global migration patterns in the coming decades. One estimate suggested around 8.7 million people could be displaced just by sea level rise globally by 2050.
8.7 million.
And the ADB study put some dollar figures on it for Asia. Countries like China, South Korea, Indonesia, they could face combined costs just from migration impacts of around $6 billion by 2080 under high sea level scenarios.
And the overall economic cost for vulnerable regions.
Economic models cited in the report predict that climate change costs, including sea level rise, in the Pacific region alone could reach as high as 12.7% of their annual GDP by 2100 under high emissions. That's devastating for developing economies.
So these are incredibly stark predictions. Are there strategies? What can communities and policymakers actually do to adapt to these unavoidable changes?
Yes, adaptation is crucial because some level of sea level rise is already locked in, regardless of future emissions. The ADB paper outlined three main approaches.
Okay.
First is retreat. This is basically planned relocation, moving people, infrastructure, communities away from inundated land. Obvious costs there are migration, resettlement, loss of place.
Socially very difficult.
Hugely difficult. Second is accommodation. This means you continue to use the vulnerable areas, but you adapt activities and structures to limit the damage. Think flood-proofing buildings, raising houses on stilts, switching to salt-tolerant crops.
Living with the water, essentially.
Yeah, kind of, yeah. And the third is protection. This is the engineering solution, building seawalls, levees, barriers, dune restoration, things like that.
The hold the line approach.
Right. And while this can seem cost-effective, especially for protecting high-value areas in richer nations, the global cost is immense. One estimate put the cost for defenses worldwide at around $500 billion over 10 years, just in marginal costs.
$500 billion.
And protection efforts aren't without downsides either. They can disrupt coastal ecosystems, change sediment flows, and sometimes displace the problem elsewhere, or create a false sense of security.
So when we look at implementing any of these retreats, accommodation, protection, what's the key takeaway? What makes adaptation actually work on the ground?
I think the core message from the ADB paper, and it resonates with other work, is that community buy-in is essential. Education, acceptance, participation by local communities. That's crucial for any strategy to succeed.
It can't just be top-down.
Yeah, exactly. There's a definite need for global cooperation, funding, technical help, especially for vulnerable nations. But ultimately, adaptation needs localization. People need accurate information. They need to understand the risks personally and be involved in the solutions for their own areas.
Making it a personal responsibility, as they put it.
Yeah, through good data and clear communication. International cooperation is vital for funding and capacity building because many vulnerable economies just don't have the resources to do this alone.
Okay, so we've covered some really big numbers today, some alarming predictions, and it's probably important to step back and remember that scientific projections, especially long-term ones, are complex. They're always evolving.
Definitely.
You see discussions online, for instance, maybe reacting to a headline about 5-meter sea level rise. People pointing out that such a rise, if it happened, would likely unfold over centuries, not, next Tuesday.
Right, the time scale is critical.
And even with something like the Thwaites Glacier, the Doomsday Glacier, which is huge and worrying, its complete collapse and movement into the ocean is generally thought to take hundreds, maybe thousands of years, even though parts of it could become unstable much sooner. Some models do suggest rapid sliding is possible for sections, but the full picture is long-term.
Precisely. It really highlights the importance of looking at the actual source data, understanding the nuances, and how scientific findings get communicated, sometimes simplified in headlines.
Yeah, context matters.
And maybe it's worth just quickly clarifying a couple of fundamental points about sea level rise itself, just to make sure we're all on the same page.
You got it here.
The two main drivers are, one, thermal expansion. As ocean water warms, it simply takes up more space.
Like liquid in a thermometer.
Exactly. And two, the melting of land-based ice sheets like Antarctica and Greenland and mountain glaciers. That water flows into the ocean and adds to its volume.
And melting sea ice, like Arctic sea ice?
That is a much, much smaller effect on sea level. Because it's already floating in the water, it's already displacing its own weight, like an ice cube in a glass. There's a slight effect because fresh water from melting ice is less dense than salt water, but it's tiny compared to land ice melt.
Right, land ice is the big one.
It's the big one. If all land-based ice melted, Greenland, Antarctica, all glaciers, we'd be looking at something like a 72-meter, or about 230-foot sea level rise globally. That's the total potential, thankfully, spread over a very long time.
Okay.
And one other weird effect. As Antarctica loses massive amounts of ice, its gravitational pull actually weakens slightly.
Really?
Yeah, less mass, less gravity. This can actually cause sea levels nearby Antarctica to fall slightly, while redistributing that water and causing slightly higher sea level rise further away in places like the Northern Hemisphere.
It's complex. Wow. Okay. Gravity itself changes. So wrapping this up, what's next in this scientific doing? Where does the research go from here? And maybe how does this deep dive inspire further learning for you, our listener?
Well, I think the studies we've talked about today really emphasize that our understanding is constantly getting better. Advancements like this physics-informed AI, these fully coupled Earth system models, they're giving us powerful new tools.
We're seeing the system more clearly.
Much more clearly. And while the full consequences of changes happening in Antarctica now might take centuries to fully play out, The decisions we make today are setting that long-term trajectory. The groundwork for future sea levels is absolutely being laid now.
Right.
These new modeling approaches are letting scientists really dig into interactions between the ice, ocean, and atmosphere that were previously too hard to study together. And as we saw with the UK model, they're identifying potential future risks in areas that maybe weren't top of the worry list based only on current observations.
A constantly evolving picture.
It really is. It's a great example of how scientific discovery keeps refining our understanding of how our planet works, especially its really critical systems.
What a deep dive today into Antarctica's changing ice. We've really seen how AI is starting to unlock the fundamental physics of how ice moves.
Yeah, that anisotropy piece is key.
How those long-term projections warn of potentially dramatic sea level rise beyond 2100 if emissions stay high.
A serious warning for the future.
And the very real economic and social impacts that coastal communities, well, everywhere, are already starting to face and will face much more intensely.
It really brings home that the decisions we make today about carbon emissions, about how we plan and fund adaptation strategies, they're going to have consequences that ripple across not just decades, but centuries.
The timescale is immense.
It is. The complexity of these Earth systems is just huge. But these new scientific tools are finally giving us unprecedented clarity into what's happening with this absolutely critical component of our planet's future climate.
So here's a final thought for you to take away. If cutting-edge AI can reveal fundamental physical properties of Antarctic ice, this anisotropy that we never fully understood before, just by looking at observational data in a new way, what other unseen complexities, what hidden rules governing our planet's climate systems might be influencing our future in ways we haven't even begun to predict yet?